Hi, welcome back to online session. In this video, we will discuss about graph coloring problem using backtracking algorithm design technique. Graph coloring problem can be exactly used in real-time scenarios like like map coloring. Map coloring in the sense to observe clearly this is the map coloring. Assume that this is a country or this is India. Assume that this is the India. India is having some number of states, distinct states. Each state is having their borders. Each state is having their borders. Now, I want to color the, I want to color in the states which are available in India with minimum number of colors that is that is done by the concept of graph coloring problem. Here, the borders are colored with different colors. Here we have been used red color, blue color, green color, and light yellowish color also I have been used total with the four different colors. I have been colored the map, given map. So why I need to color the map in the sense to identify the distinct to identify the distinct areas with the color it is possible. That's why we need to do coloring. Next one is where exactly we use graph coloring problem is scheduling the task. If you want to schedule different tasks to the same person at the time, each and every schedule should not be same, it is distinct. To identify the variation of each and every schedule in a distinct mode, we need to apply coloring. So once we can apply the coloring, so by identifying the coloring, we can say that it is a distinct work or distinct task. Next, as usually in universities or colleges, we frequently using graph coloring problem whenever we are preparing timetables. So whenever we are planning to prepare master timetable, so at that time in a week there are 6 days, 6 working days. But let me tell you, Monday, take a day Monday. So if you want to schedule the master timetable of Monday, assume that there are four different sections, section A, section B, and section C. To identify the master schedule in a distinct mode, you need to color it with four different colors in a particular day. So the coloring, graph coloring problem will work very efficiently whenever you are planning to prepare timetables, master timetables. And also we use for preparation of the assignments also we use graph coloring problem. Next important application of graph coloring problem is Sudoku. This is the game. We can call this one as a Sudoku game. So in which we need to color each and every vertex with different colors by satisfying some constraints. That is called as a graph coloring problem. That is called graph coloring problem. In pseudocode diagram, if you clearly observe that no two adjacent vertices should not have the vertex of two adjacents in the given graph should not be colored with the same color. So you can color the graph in such a way that all the vertices in the graph can be colored in such a way that the edges of the vertices should not have the same color. So in such a way we need to color the vertex. So these are various notable and important applications used in graph coloring problem. Next, let me tell you what exactly graph coloring. So what is mean by chromatic number and what is the degree of the graph? Let me tell you in this session. Now, first we need to learn what is the definition of graph coloring problem. Graph coloring is a problem. It is a problem. What to do? We need to color each vertex. We need to color each vertex in the graph. In the graph. Consider there is a graph. The graph can contain some number of vertices which can be identified in a circles. Always the vertex can be identified, drawn in the form of a circle. In a graph, if any circle, if you can form, those circles is considered as vertices. And the graph coloring problem is a problem of coloring each vertex in the graph. How you can color it is we will discuss. In such a way that no adjacent vertices have same color. No adjacent vertices have same color. So now let me tell you the graph. Consider that this is the graph. This is A. These are all the vertices. Assume that these all are vertices. The vertices can be drawn with circles. So there are three circles. These three circles will be considered as vertices, vertex 1, vertex 2, and vertex 3. And we need to color the vertices, all three vertices, in such a way that no adjacency vertices have the same color. So this is the vertex and this vertex adjacent vertex is this is another adjacent vertex and this is also adjacent vertex of this one. So that means that I need to color the given graph with three different colors like red, green, and blue. So when I can color the graph with the red, green, blue, in this case, so the condition is satisfied. No adjacent vertices have same color. No adjacent vertices have same color. In this way, I have been colored the given graph. So first one is the red. So we can color it with red, fully red. Next, green, color it with green. You need to color the graph vertices. You need to color the vertex with green, and one more graph is there. One more vertices is there. You need to color the remaining vertex with blue. So here, if you consider the adjacent vertices, so no adjacent vertices have the same color. That's why this is considered as the graph coloring problem. And here, how many number of colors we are used? That is called m colors. Here we are using m number of colors. That's why instead of graph coloring problem, I can say it is renamed as m coloring problem. Students both are same. In examinations, they may ask the question, solve m coloring problem. M coloring problem in the sense graph coloring problem. Both are same. Here M will indicates the total number of colors required for coloring the graph, that is called as a M coloring graph. So this problem is also known as M coloring problem also. Okay. Next important thing is degree of the given graph. What is mean by degree of the given graph? So the degree of the graph can be defined with the word D. D stands for degree of the given graph. Okay. Then we can color it with D plus one colors. So let me try the degree of those. Now assume that this is the graph. If you assume this is the given graph, the graph can contains three vertices, vertex 1, vertex 2, and vertex 3. Now tell you, so what is the, let me tell you what is the um, degree of the given graph. So degree of the given graph in the sense how many number of vertices and each, how many number of ways each and every vertex is having. So the given vertex, this is the first vertex. The vertex is having two outs. This is one out. This is another out. So the degree is 2 here. For this vertex, the degree is 2. This is one out. This is another out. So the degree of this vertex also 2. The degree of this vertex is 2. This is one out. This is one out. So finally, I can say the degree of the given vertex is the given graph is 2. So D is equal to 2. But total how many while coloring the given graph with m number of colors? So I required minimum D plus 1 colors I require. That means that 2 plus 1 colors I require for coloring the given graph. That means that total number of colors required are 3. Total number of colors required to color the graph are 3. So here I have been colored the given graph with 3 colors, namely the first color is red, second color is green, and the third color is blue. So in this way the given graph I have been colored with 3 minimum number of colors, namely red, green, and blue. So in this way we can calculate the find the degree of the graph. Next, what is mean by chromatic number? So now we will see the definition of chromatic number. Chromatic number means that the least number of, that means that minimum number of colors needed or required to color the given graph. That means that the minimum number of colors required to color the given graph is known as chromatic number. If you assume the given graph can be colored with three different colors, namely red, green, blue. So by satisfying the concept or constraints of graph coloring problem, finally I can say the chromatic number of the given graph is 3. The chromatic number of the given graph is 3. Why? Because the minimum number of colors required to color the graph are 3. Those colors are red, green, blue. So students, in this slide, we learn what is meant by graph coloring problem and what is the another name for graph coloring problem, that is called M coloring problem, and how to calculate degree of the given graph, and how to find chromatic number of given graph we discussed in this session. Now we will discuss another example here. Here, consider a graph. This is the graph. Now I need to find the degree of the graph. So I want to find the degree of the graph. How to find the degree of graph? if you want to find the degree of the graph, let me take a table. Let me take a table. In that table, so we will discuss how to find the degree. Now take the vertices. How many vertices are there? So this is one vertex. The first vertex is M, and the second vertex is A, and the third vertex is T, and the fourth vertex is H. So let me take four vertices, namely M, A, T, H. M, A, T, H. These four are considered as vertices. Vertices. Now, if I want to find the degree of vertex M, how to find the degree of vertex 1? If you want to find the degree of vertex M, let me consider how many outs from M. This is one out. This is one out. Okay. This is another out. This is another out. This is another out. This is 3. So total number of outs of vertex M is 3. Now let me consider how many number of degree, what is the maximum degree of vertex A. So if you consider the vertex A out 1, this is one way of moving out 2, this is another way of moving out 3, this is another way of moving out 4, out 4. And this is another way of moving out 5. So the degree of vertex A is 5. So the maximum degree of vertex A is 5, can be generated from the given graph. Now let me take the vertex of T, how many outs? So this is one out, this is another out, 2, and this is another out, 3. So the maximum degree of vertex T is 3. Now let me find the degree of vertex H. If you consider H is in a vertex, so the number of outs are one out. This is the second out. This is the third out. And this is the fourth out. And this is the fifth out. So total number of the maximum degree of vertex H is 5. So in this way, I have been found the maximum degree of the vertices, the maximum degree of the vertex, the maximum degree of the given graph is 5. Here, the maximum degree of vertex is 5. So the degree of vertex is 5, that can be represented with capital D. So capital D equal to 5. So here D plus 1 number of colors are required to color the graph. That means that the total number of colors required to coloring the given graph are 6, which can be represented as chromatic number. Here 6 can be represented as a chromatic number. So to find the degree of the graph, figure out all the vertices degrees. I have been figure out 4 vertices. The degree of the graph will be its largest vertex degree. Hence, the largest vertex degree is 5. Hence, 5 is to be considered as the total network degree capacity, that is 5. So, if you want to color the given graph by applying graph coloring problem, the minimum number of colors required are 6. Why? Because D plus 1 we will get 6. The 6 value is to be considered as a chromatic number. 6 is considered as a chromatic number. Students, in this way, you can find or find the degree of the given graph. Now let me tell you one example how to color the given graph. So consider this is the question. The question is there is an undirected graph is given. This is undirected graph. That means that there is no directions. It is considered as both directions. No directions are given. So this is considered as undirected graph with maximum degree d. So the degree of the given graph is d, and find graph coloring using at most d plus 1. Find graph coloring using at most d plus 1. Now let me calculate the degree of the given graph. So now let me calculate the degree of the given graph. So I want to calculate the degree of the given graph. So now how to calculate the degree of the given graph? Let me take a single vertex. Consider this is the vertex. From the given vertices, how many outs are there? This is one out. This is second out. This is third out. Let me take any one. If you consider any one of the vertex. So the number of outs from the given vertex are one out, two out, three out. So even if you consider any one of the vertex randomly, each vertex will take three number of degree. So hence the maximum number of degree of the given vertex d is 3. So the maximum degree of the given graph is represented with the keyword d, that is equal to 3. So, but here we need to color the given graph with maximum number of colors, that is d plus 1. That means that total number of colors cannot be exceed 4. So that means that the chromatic number of the given graph is 4, which can say that minimum number of colors required to color each vertex in the given graph. So the main objective is you need to color the given graph with minimum, with maximum 4 different colors only. With maximum 4 different colors only. So here assume that this graph maximum degree is 3, and totally we require 4 number of colors to color the graph. So if you consider the graph, so this is the vertex is colored with blue, this vertex is colored with green, this vertex is colored with yellow, and this vertex is colored with red. If you consider the adjacency vertices in the given graph, no two adjacency vertices should not have the same colors. No two adjacent vertices, no two adjacent vertices have the same color. That means that if you consider any vertex, any two vertices, those two vertices should not color with the same color. If you consider this is the edge, so this is the edge. This vertex is colored with blue. This vertex is colored with green. So like that only, any, if you observe any vertices, no two vertices have the same color. So the given graph is to be colored with 4 colors, namely red color, green color, blue color, and yellow color. And yellow color. So the minimum number of colors required for coloring the given graph is 4. Minimum number of colors are 4. Hence the chromatic number Cn equal to 4. Minimum number of colors required to color the given graph is 4. So students, in this way we need to calculate or find the degree of the given graph and the chromatic number of the given graph you can find very easily. Now we will discuss about what is mean by chromatic number and find the chromatic number of the given graph we will discuss in this session. This is very important definition. Chromatic number definition is minimum number of colors needed to color the vertices of a graph in such a way that no two adjacent vertices have same color. Now consider this is the graph. The graph can contains four vertices, namely the graph can contains four vertices, namely vertex A, vertex B, vertex C, and vertex D. Assume that this is the given graph. The graph can contains four vertices, and you need to color each vertex with you need to color each vertex by satisfying the conditions. No two adjacent vertices should not have the same color. And finally, you can minimize the number of colors to color the given graph. So here, if you observe here, what is the degree of the given graph? Now let me calculate the degree of the given graph. So the degree of the given graph D I need to calculate. If you consider vertex A, how many outs are there? There are three outs. One, two, three outs. If I consider vertex D, the number of outs are one, two, three. Even if you consider any one of the given vertex, given graph, any one of the vertex from the given graph, each vertex can take the maximum degree is 4. Hence, D is the maximum degree is 3. Hence, the value of D is 3. So, the degree of the given graph is 3. Okay. So, the degree of the given graph is 3. But you need to color it the given graph with the maximum number of colors that is equal to D plus 1. That means that you may color the given graph with maximum number of colors. Those are four colors. That is considered as chromatic number, CN, chromatic number. So the chromatic number of the given graph is 4. We need to color the given graph with the four different colors, namely orange color, blue color, green color, and also this is red color. So in this way, we need to color the given graph with different colors. Okay. So now let me take one more example. Consider this is another example. If you consider the given graph, so what is the degree of the given graph? The degree of the given graph, if you observe clearly, so maximum number of outs for each and every vertex we need to calculate. If you consider this is the vertex, if you consider base vertex, the number of outs are 1, 2, 3, 4. So even if you consider any one of the vertex, number of outs are 4. Hence the degree equal to 4. D value is equal to 4. That is D. D value is 4. And maximum number of colors required to color the given graph will represent D plus 1. That is equal to 5. You need to color the given graph with the minimum number of colors, that is 5 number of colors. Hence 5 is to be considered as chromatic number of the given graph. Chromatic number of the given graph. Friends, in this way we need to find or calculate or identify the minimum number of colors required to color the given graph. I hope you understood how to calculate the degree of the given graph and how to find chromatic number of the given graph clearly. We have been discussed with the two more examples also. Now let me discuss what are the basic principles we need to adopt before solving the given graph coloring problem by using uh, backtracking technique. Now, let me see how to solve the given problem by using backtracking technique. By using backtracking technique. The backtracking is an algorithm design technique which can be used to solve the given problem with the minimum number of steps. With the minimum number of steps. Okay. Now, once again, we will brush up the concept of graph coloring problem. The main objective of graph coloring problem is we need to fill the vertex in the given graph. You need to fill all the vertex or vertices available in the given graph with the minimum number of colors by satisfying the condition no two adjacent vertices have same color. So here you need to color all graphs, sorry, all vertices with colors, minimum number of colors required for coloring all the vertices in the given graph can be considered as chromatic number. Chromatic number in the sense the smallest number of colors required to color the given graph is called as a chromatic number. Hence, graph coloring problem is to be considered as NP complete problem. NP complete problem in the sense non-polynomial complete problem. Non-polynomial complete problem. So now let me try how to apply backtracking technique to the given problem. We will see how to apply backtracking technique to the given problem. Now we will discuss in this session. Okay. When I can apply backtracking technique to the given problem, let me tell you the step-by-step procedure how to solve the given graph coloring problem. So by using the backtracking method, the main idea is to assign colors one by one to different vertices right from first vertex. That means that we need to color all the vertices with different colors starting from vertex 0. That is not starting from initial vertex. We need to take and start coloring each vertex one by one vertex with different colors. And before coloring or before assigning a color to a particular vertex, before color assignment, let me check if the adjacency vertices have same color or different color. The adjacency vertices have same color or different color, we need to verify it by considering already assigned colors to the adjacency vertices. Okay. If the color assigned does not violate any constraints, here the constraint is no two adjacent vertices have same colors. This is the constraint or rule of graph coloring problem. If the color assignment does not violate any constraint, then we mark that color as part of the result. If color assignment is not possible, if color assignment is not possible, then what to do? Backtracking we can apply and we can return false. We can return false. So that means that if the given graph, if any two adjacent vertices having colored with the same colors, if this type of scenario occurs to you, in this case, you simply apply backtracking technique for that adjacent vertices of the given graph. When you apply backtracking technique, then it will return false condition. So you can continue the same procedure, apply the backtracking technique once again. So keep on applying backtracking technique till all the vertices in the given graph are to be colored by satisfying the condition, no two vertices can have, adjacent vertices can have the same color. So in this way, we need to color each vertex in the given graph with different colors. Now let me explain the given problem, how to solve the problem. Consider this is the problem. In the given problem, the graph is to be considered as undirected graph. And color, we need to color all the vertices with colors. So here what are the various vertices available? Vertex A, vertex B, vertex C, vertex D, vertex E, and vertex F. These are these are vertices. And the problem solution is you need to color all the vertices with different color by satisfying the condition. No two adjacent vertices have the same coloring. No two adjacent vertices have the same color. So before solving graph coloring problem, you need to find or calculate the degree of the given graph. What is the degree of the given graph? You need to find. And what is the chromatic number of the given graph, which means that the minimum number of colors required to color each and every vertex in the given graph. So once you can finalize the chromatic number and degree of the given graph, then we will solve the given problem with an example. Now let me try to find the degree of the given graph. If I want to find the degree of the given graph, so I can start with vertex A. If I can start with vertex A, so how many possible outs? There are two possible outs from A. This is one out, this is one out. The possible outs for A is 2. And what are the possible outs for C? For vertex C, the possible outs are 2. This is one possible out, this is another possible out. The total number of possible outs are, sorry, C2. For B also 2. This is one out, this is one out. So if you consider D, the number of possible outs are 2. This is one out, this is another out. So this is 3. For E also, if you consider vertex E, number of possible outs are, this is one out, this is another out. If you consider the last vertex F, the number of possible outs are 2, 1 and 2. So if you observe the number of possible outs for each and every vertex clearly, if you observed here, all vertices are having equal number of degrees. So hence the maximum degree of the given graph is 2. The maximum degree of given graph is 2. So that is D value is 2. D value is 2. So once you can find the value of D, then you can find the value of Cn. The value of Cn equal to D plus 1. How to find Cn? D plus 1. D plus 1 stands for D is degree plus 1 3. So you need to fill the minimum number of number of sorry minimum number of colors colors required to color the given graph is called as a chromatic number. Minimum number of colors required to color the given graph is called chromatic number. Hence, chromatic number equal to 3. So that means that you can fill the given graph with maximum number of, not minimum, sorry, maximum number of colors required to color the given graph is 3. So maximum number of colors required are minimum number of colors to fill the each and every vertex is 3. So you can take red, green and blue. Now you can fill all the vertices A, B, C, D, E, F with the standard colors, namely red, green, blue. Now let us see how to solve the given problem by using backtracking technique we will discuss. Okay. So this is the given graph. This is the given graph. In the given graph, when I can apply backtracking technique to the given graph, consider all the vertices. Let me start from vertex A. Let me start from vertex A. If I consider the vertex A, initially I have been colored the vertex A with red. I have been colored the vertex A with red color. So now we will see the vertex A is to be colored with red color. So, sorry, here we will take this one. The vertex A we will color with red color. So vertex A is to be colored with red color in the first step. Next, move to another one. Move to next second graph. Here I have been colored only one vertex. So this vertex is already colored with red. Next, adjacent vertex to A is B. Adjacent vertex to vertex A is B. Now I need to color the vertex, another vertex. I need to color this vertex with another color that is called green. I have been colored the vertex B with green color. I have been colored the vertex B with green color. If you consider the path between A to B vertices, this is considered as adjacency vertices. So here, what is the constraint of graph coloring problem? No two adjacency vertices can have the same color. No two adjacent vertices have same color. So here, if you observe these two vertices A and B, those two vertices can be filled with a different color, not with the same color. So it was satisfying the condition. Next, move to third vertex D. Third vertex D. Now here already first vertex is filled with red. Second vertex is filled with green. Now I need to fill the third vertex. I need to fill the third vertex. So here, this vertex, third vertex, I can fill with green. Can I fill with green? No. If I filled this with green, these two vertices are same. It is not satisfying the condition. Hence, I cannot fill this with green. I cannot fill this with green. Hence, remove green color. So next, can I fill it with the blue color? Yes, you can color it with the blue. Can I color it with red? Yes, you can color it with red. Red color already I have been colored here, but once again you can use red color. Even if I filled with red color, no two adjacent vertices have the same color. It satisfies the condition. So here, this is also vertex D also colored with red. So if you observe clearly, these two vertices B and D cannot have the same color. Those are filled with two different colors. Hence, it is also satisfying the condition. Next, move to another vertex. So three vertices are colored with the different colors: red, green, red. If you observe, no two colors have the same. No two colors have the same. Remember this. This is very, very important. No two vertices have the same color. Okay. Next, move here. Next, move here. This was already colored with red and vertex B already colored with green. Next, vertex D already colored with red. Next possible way of coloring F. So I can color the possible ways. I can color F with either green or blue. Either green or blue. I can color the F vertex with either green or blue. So, but here I can consider I have been filled the vertex F with green. Okay. Next, moving on to the next vertex. Let me try. Which color is used to fill vertex E? Vertex E. So A was colored with red. B is colored with green. Already B was colored with green. And vertex C is colored again with red. Vertex D is filled with already filled with green, but all the vertices satisfies the condition here. All the vertices have been satisfied the condition that no two adjacent vertices have the same color. Blue color I have been filled. Next, move to another vertices C. Here C only left here, only C left. Can I color with red? Can I color with red? What will happen? I will see. If I will try to color with C red, cannot be possible. Why? Because no two adjacent vertices cannot be filled with the same color. Hence, you cannot fill C with red. You cannot fill C with red. That means that you cannot be able to fill C with red color. Next, can I fill C with green? I will see. Let me see. Can I color with C with green? If I color C, vertex C with green, what will happen? This is an edge. No two adjacent edges have the same color. No two adjacent vertices cannot be filled with the same color. So green color also not possible to fill. Hence, do not apply green color for C. Green color, do not apply green color for filling C. So green also not possible. Can I color C with blue color? If I can apply C with blue color, these two vertices okay, these two vertices okay. If you consider these two vertices, two adjacent vertices filled with the same color, blue. So hence you should not color C, vertex C with blue color. Hence stuck here, apply backtracking technique. That means that you cannot have the possibility of filling the vertex C with red, green, blue. So you cannot fill red color, green color, blue color. Either green color, red color and blue color cannot be possible to fill the color of given vertices C. Hence, what will happen? What will happen? We have been struck here. Where we struck here? We have been struck at vertex C. So struck here. Once you struck here, what will happen? Cannot assign any color. You cannot assign red color. You cannot assign green color. You cannot assign blue color. What is the degree of the given graph? The degree of the given graph is 2, and you can color the given graph with maximum number of colors, that is d plus 1 colors. That means that you have the provision for coloring the given graph with maximum number of colors are 3. So but all maximum number of colors are already used here. But if you color with a different color, the maximum number of colors will be exceeded. But to overcome the problem, what you will do is, now you can simply apply backtracking technique to vertex C. Apply backtracking to vertex C. So you need to apply backtracking to vertex C. Once I can apply backtracking to vertex C, what will happen? We will see. Okay. Now apply backtracking to C. What will happen? We will discuss now. Okay. Uh, okay. Now here we have been stuck. Now we are applying backtracking technique in sixth. Here, in sixth position, we need to apply backtracking technique to the given vertex. The vertex is C. Once I can apply backtracking to vertex C, so here I have been structured. So once I can apply backtracking technique here, what will happen? We will discuss here. Now simply say that apply backtracking technique. Apply backtracking technique. Simply apply backtracking technique to the given vertices C. Apply backtracking technique to vertex C here. Once you apply backtracking technique to C here, what will happen is now go back, moving back to here, and you need to change the color of E. Earlier, the vertex E is filled with the color blue. Now, instead of blue color, you can color with some other color. If you color with this color, even if you color you cannot color it here. Can I color it with green? Green color not possible. I cannot color E with green color. Sorry, students. Wait for 2 minutes. I will explain clearly. Can explain clearly. Spotlight. Text. Right. Draw. Yeah. Yeah. Here, the problem with here the problem is with the C, vertex C. Problem with the vertex C, we have been structured here. Now we simply apply backtracking technique to the given graph. If you apply backtracking technique to vertex C, then go back to E. Backtrack when we apply backtracking technique to C, go back to E. And here think once, already the vertex E, already here the vertex E is colored with blue. So we need to change the color of blue, what we filled with earlier. So in place of blue, can I fill with green? G? No, green color not possible. Why? Because here F also filled with green color. Green color I cannot be filled with here. Can I fill with red color? No, you cannot fill here E with red color. Why? Because D is filled with red color. If you fill E also red color, no two adjacent vertices have the same colors. So R also not possible. So you have the possibility only B, but B also not possible. Hence again apply backtracking technique to E. Once you can apply backtracking technique to E, go back to F, then go back to F. So now we moved here. So here, instead of green color, can I apply with red color? No, I cannot apply to fill vertex F with red color. Why? Because the vertex D is filled with red color. So I cannot fill the vertex F with red color. So next the possibility is, can I color the F with blue color? Yes. Yes. You can have the provision to color the given graph with the color of blue. With the color of blue, you have the possibility. Even if you fill the vertex F with the blue color, there is no problem. So that's why, so instead of filling F with green, I can fill the color with blue, which was highlighted here. So now let me consider F was colored with blue. So once I have been colored F was with blue, next I can move to E. Here, um, so can I color E with red? No, E cannot be colored with red. Can I color with E with B? No, E cannot be colored with blue. Can I color E with green? Yes, you can color E with green, no problem. Can I color A with red? No, you cannot color, sorry, C with red. Red you cannot be color it. Green also you cannot be color it. But you can color B with, you can color C with blue. You can color C with blue. So you got the solution. This is the final result. you got the solution. In the solution, in the given graph, there are how many number of vertices are there? A, B, C, D, E, F. These vertices you can color with minimum number of colors. Those colors, namely red color, green color, and blue color. RGB colors, we can say these are standard RGB colors. Hence, I can say the minimum number of colors to color the given graph is considered as chromatic number. Chromatic number of the given graph is 3, and the degree of the given graph is 2. The degree of the given graph is 2. The chromatic number of the given graph is 3. So in this way, you can color the given graph with different colors. Now, let me draw the final answer. Let me draw the final answer. Red color with, sorry, I can take the thickest one. Let me color with red. First one with red. D also colored with red, and B is green. The vertex B was given colored with green and blue. Vertex C, vertex F are colored with blue. If you consider any two vertices, if you consider any two vertices A to B, if you consider A to B, no two adjacent vertices have same color. Satisfy the condition. If you consider A to C, if you consider no two adjacent vertices have the same color, it is satisfied. Consider BC. Consider BC. No two adjacent vertices have the same color. Consider DF. No two adjacent vertices have the same color. Consider FE. No two adjacent vertices have the same color. Consider EC. No two adjacent vertices have the same color. Consider BC, vertex B to vertex C. No two adjacent vertices have the same color. Consider DE. No two adjacent vertices have the same color. So even if you took any two vertices, you will fill the given graph with a minimum 3 number of colors. So hence the chromatic number of the given graph is 3. The chromatic number of the given graph is 3. You can color the given graph with red color, green color, and blue color. Red color, green color, and you can color with blue color. So the final result I have got. But how many number of times I have applied backtracking? I have applied backtracking for vertex C. I have applied backtracking for vertex E also. 2 times I have been applied backtracking. Once applied backtracking, go back. So backtrack 1, backtrack 2. 2 times I have been applied backtracking to the given graph. Finally, I will get the optimal solution. So I will get the optimal solution finally. So this is the resultant matrix. Okay. Students, this is the final answer. Hence, the graph coloring problem is to be solved with minimum number of steps. How many number of steps we have been used to color the given graph? Here we simply used the total number of steps. If you observed clearly, 1, 2, 3, 4, 5. 5 steps we have sorry, 6 steps we have used to find the optimal solution of the given graph. Okay. So this is the graph coloring problem algorithm, backtracking algorithm. So let me explain this algorithm. Name of the algorithm is M coloring. M coloring. Why I can consider another name for graph coloring is M coloring. M in the sense M number of colors required to color the given graph. That's why in examinations they may ask both graph coloring and M coloring both can be considered as same. Both can be considered as same. Okay. So here M coloring is both are same. Here K, consider K. K stands for the vertex indices. This is the vertex. The vertex indices will represent K. Okay. So here x of K in the sense, x of K in the sense, it will indices legal colors, all legal colors. Legal colors in the sense, red color, green color, yellow color, these are considered blue color, these are considered as legal colors. You can assign any legal color to the given vertex. If no color exists, that means that if any one of the vertex is not to be colored, then you can assign x of k equal to 0. X of k equal to 0 means no color is to be assigned to the given vertex. Same, you need to calculate the next value. Always try to assign or fill which color you need to identify the new color, and you need to fill the vertex with which color. That is the question. In each and every stage, we need to think once again, and we need to assign which type of legal color to the given vertices. We can think that. If no new color is possible, x of k is equal to 0. If no new color is to be possible, then what to do? You can apply backtracking technique. Then you can print, you can change the previous colors. Then you can fill the vertex with the new color. Okay. So here we are used one function, that is next value of k. That means the assign x of k is a legal color. So we don't know which color we need to find. We need to fill the vertex with which color we don't know initially. That will clearly explain in the linked algorithm. So here that linked algorithm is to be clearly described here. Okay. So this is the linked algorithm. So I have been used the function next value of k in M coloring problem algorithm. So that's why when this statement or function is to be executed, control is directly moved on here, and this algorithm is to be executed. Once this entire algorithm is to be executed, and keep on working the remaining statements. So now let us see how this function will be working. Next value function is to be working. So this algorithm clearly says that which type of color is really required to fill the next vertex. So let me discuss here. Okay. So here, if you want to obtain a new color or next color to the given vertex, you have a formula, that is x of k equal to x of k plus 1 mod m plus 1. M is nothing but degree, the degree of the given graph plus 1. That means that maximum number of colors required to color the given graph will be depends on the degree of the given graph, that is M or D. Okay. If f of x is equal to 0, then return. That means that if there is no color is fine, apply backtracking technique. So you need to find or compare each and every adjacency vertices are filled with the same color or not. If you want to fill the adjacent vertex with the same color, you do not fill it. Simply ignore the color and go for new color. Okay. So in this way, you can able to find the next color, and we can color all the possible vertices of the given graph with number of colors, that is m number of colors. So this is the algorithm. So this algorithm is required for represents the step-by-step procedure to color the given graph. Now we need to analyze the time complexity and space complexity of the graph coloring problem. So the time complexity of graph coloring problem, we can say in terms of vertices and number of colors, that is m power v, order of m power v. Order of m power v is the time complexity, and order of v is the space complexity. So the space complexity in the sense the total space required to keep the vertices in the given graph, it will be depends on the size of the number of vertices. Total number of vertices can be available in the given graph is the space complexity. For sorting the output array in order of V space, the total space complexity is order of V, whereas the time complexity of the given graph is order of m power V, order of m power V. Since backtracking is also a kind of brute force approach, there would be total order of m power V possible colors combinations. This number of color combinations required to color the given graph. Hence, it is to be noted that the upper bound time complexity remains the same, but the average time taken will be less due to redefined approach. Redefined approach. So simply I can say time complexity is m power V, space complexity order of V, order of V. Now we came to the end of session. Now I am concluding that. So this graph coloring problem is play a vital role in the market nowadays. Whenever you are planning to coloring the maps of India state or some other state, the map of some countries. If you are to distinct the timetables, if you are to distinct the colors with the pseudocode games, this will play a vital role. And also the graph coloring problem is mainly depends are working on the principle of the degree of the graph and the chromatic number of the graph. The degree of the graph can says that the maximum number of outs of the given graph can be represents the degree of the graph. Once you can find the degree of the graph, that is d, and you can add one more value d plus 1. D plus 1 in the sense that is considered as chromatic number. Chromatic number is nothing but minimum number of colors required to coloring the given graph. All vertices is called as a chromatic number. By satisfying the constraints, no two adjacency vertices in the given graph can color with the same color. That is called as a graph coloring problem. So hope you all are understood the concept of graph coloring problem. So next we will discuss about Hamiltonian cycle problem in the next class. Students, in fifth unit, you should be focused on 4 questions. Definitely, you may expect the questions from university examinations. One question from n queen problem, either 4 queen problem or 8 queen problem. You may expect one question from that one. Otherwise, you may expect the question from graph coloring problem as well as Hamiltonian cycle problem also. Hence, my sincere request is so be careful while preparing the examinations. You should not neglect these concepts. Okay. Have a nice day. Thank you. Thank you.